Welcome to Required Derivations number 7. The topic is energy and work. I'll start off by identifying what we refer to as the equation of greatness, in which the work done by a force can be determined if the force is a constant force using the force value times the displacement. Of course, this work done by the force will cause an increase in the kinetic energy at the expense of the potential energy. So as an example, if an object is accelerating downward due to the gravitational force, the work done by the gravitational force is going to be seen as an increase in the object's speed. Of course, all the while the gravitational potential energy is decreasing. So the increase in the kinetic energy comes at the expense of the gravitational potential energy. When we write the equation of greatness in its full form here, I've done it in red, you see the outside terms, the minus delta gravitational potential energy, or just potential energy, and the force times the displacement can be equated. And solving that equation for the force, one sees that the force is really just the change in the potential energy divided by the change in the position. This often is a slope calculation on a u versus x or a u versus r graph. If the force is constant, then one may use the delta symbols. If the force is variable or a function of the position, then one must, in order to find the force, take the derivative of the potential function with respect to that particular spatial variable. Frequently that's x or r. One thing that you should remember is that the force is the negative of the derivative of du dx. Here is an example of an arbitrary potential function as a function of position, u versus x or u versus r. And I've identified several positions: x0 meaning the equilibrium position, x1 to the left of it, x2 also to the left, and x3 to the right. And the accompanying values of the potential energy at those positions. If one recalls that the force is equal to minus du dx, or the force is the negative slope of the u versus x graph, then if you notice all the positions left of the equilibrium, the slope is negative, which means that the force is positive. And since the slope at x1 is steeper than the slope at x2, then the strength of the force at x1 is greater than x2. The further the particle gets from the equilibrium position in either direction, the stronger the force that it feels in this graph, because the slope is getting steeper. At x equals x naught, the slope is 0, which means the force is 0. This is often accompanied by the object having its greatest speed. And for all points to the right of x naught, then the slope is positive, which means that the force is negative. Taking a look at the same graph, let's assume that the particle is just to the right of our equilibrium x naught and is moving to the right. Since it's moving to the right, the slope is positive and increasing, which means that the force is negative and getting stronger. Since the force is negative, the acceleration is negative because of F net equals ma. Since it's moving in the positive direction, but its acceleration is negative, the particle slows down. Eventually the particle will stop and turn around and begin moving left, but it is still to the right of x naught. Now the force remains negative since the slope is positive. The acceleration is negative since the force is negative, but the velocity will be negative since it started from rest and had a negative acceleration. So the object will speed back up toward the origin, or return to the middle of its oscillation. Of course, now the magnitude of the force is diminishing to 0 when it is at the equilibrium position x naught, which of course is when it achieves its maximum speed. Here is a nice example where one can employ the equation of greatness for energy. A 3.5 kilogram block moving along the x-axis is acted upon by a force that is a function of x, as stated in the equation where the constants A and B are given. At a position of 1.6 meters, the block is moving to the right with a speed of 4.5 meters per second. Determine the speed of the block when it is at a new position, 2.3 meters. The solution requires that since this force is a function of x, we can integrate that function of x from the first position to the second position. Of course, it has two terms, hence I have two integrals in this equation. And when one evaluates that, one determines the amount of work done, which can also be expressed as a decrease or a negative change in potential energy. Of course, employing the equation of greatness, this change of negative change of energy is equal to a positive change of kinetic energy. And so we can just directly set that delta K equal to the same value. And if we want to know what the final velocity is, and we know the initial velocity along with the mass, then we can use algebra to determine the final velocity. So this example is an example where one can employ the equation of greatness. This particular slide demonstrates how forces that are functions of position can be used to determine the work done by this force when an object moves from initial position to a final position. And so the functions are different functions of x, and of course the amount of work done is simply the integral of f dot dx. Since f is in the x direction and dx is in the x direction, the dot product drops out. And so one can practice their integrals in this calculation of work to determine how much work is done. Of course, these values are equal to the change in the kinetic energy as dictated by the equation of greatness. Here is one final example where we have a variable force, which is a function of position. F of x is equal to 3x squared minus 4x plus 5. And we're told that the speed of the object is 5 meters per second at a position of 1 meter. And we're asked to determine the speed when it is at a different position of 3 meters. So, of course, we use our force function to determine the amount of work done by this force in moving the object from 1 to 3 meters. And we see that after doing the integration, we get 20 joules. This 20 joules then can be set equal to the kinetic energy change, and from that we can find the final velocity of the object.